and welcome back to this online short course by Red Door Analytics, Survival Analysis and Introduction to Concepts, Methods and Software. Today we'll be talking about the Cox model or the Cox proportional hazards model. So the Cox model is one of the most widely used survival analysis models. It's also known as the Cox proportional hazards model. And it has the same standard formula as the other survival models. So in the previous section, we spoke about the standard survival regression models, and it looks very similar to what I'm presenting here, where we have that the hazard rate here is a function of time and covariance x. And this is equal to a baseline hazard rate as a function of time t, multiplied by the exponential of covariance x multiplied by beta, their coefficients, which are log hazard ratios. So the important thing to know with a Cox proportional hazards model is, despite the similar formula, there are some differences to be aware of compared to the previous models we spoke about in the context of parametric survival models. So this model is known as a semi-parametric approach, since the baseline hazard function, lambda naught t, is not actually estimated. This value, this function, is allowed to vary over the time scale, so we don't make the same assumption as the other parametric models, where we either had a constant function across the time scale, or we allowed it to vary in the way that the Weibull model does. So it is allowed to vary across the timescale, but it's not directly estimated in the model, meaning that we can only estimate relative effect measures, i.e. we only estimate hazard ratios from this model, and we don't actually estimate any absolute effects or hazard rates. But do note that although we do only estimate directly from the model hazard ratios, there are methods that you can run or implement after you have fit a Cox model to estimate any relative effect measures, such as hazard rates. But it isn't done automatically in the Cox model. So that some of the background to this is that instead of maximizing the likelihood, as is done in other parametric survival models, Cox models are using something called the partial likelihood. And I won't go into detail here. If you're interested in knowing a bit more about this, you can read some of the background research around this, and there's some references at the end of this section. But what it means is that this allows for the estimations of hazard ratios without the need to directly estimate the underlying hazard rates or to assign a shape to the hazard rates, which that's very nice. We don't have to assign any sort of shape to these hazard rates. So although this model does not directly estimate absolute rates, these can be estimated after the model fit-in procedure, as I said previously. And the proportional hazards assumption, which comes directly with the Cox model, can be relaxed, but the standard Cox model makes something called the proportional hazards model, hazards assumption. And this is something that we will cover in the next sections of the course. But to fit a Cox proportional hazards model in Stata, we can use the stcox command. So this is what we would do if we were interested in, now we're going back to our example of our breast cancer patients in Germany, where we are following them from breast cancer diagnosis until an event, where event is either deaths or reoccurrence of their breast cancer. And we're interested in looking at the exposure of hormonal therapy and how that affects our outcome. So here we have stcox. We tell Stata we want to fit a Cox proportional hazards model. And then we tell Stata that we're interested in the effect of hormone. That's our hormonal therapy variable, which is 1 when patients have received hormonal therapy and 0 otherwise. And then this option, no log, is just a display setting for the output. So this is the output here. We have lots of information at the top of the output. But the thing that we're really interested in is the output in the table here, where we see that we have an estimate of the hazard ratio for our variable hormone. We no longer see an underscore cons out in this output, which is what we saw previously when we used SDReg. And that's because, as I said, we do not directly estimate the baseline rate in this model. This isn't something that's estimated. But we do get a hazard ratio, and we get a p-value for this inclusion of this variable and a confidence interval here. So we see that the hazard ratio is 0.69 from the Cox model. This means that the rate of recurrence of breast cancer or death of those who received hormonal therapy is 0.69 times that of those individuals who received no therapy. And we get a hazard ratio that's constant over time here. You can see what this looks like. We have hazard ratio on the y-axis, and on the x-axis, the time since breast cancer diagnosis. We see that we have 0.69 is our line, and it's constant across the whole of the time scale. Now, how does this compare to what we estimated previously? Well, when we estimated our hazard ratio from our exponential, our Weibull, and our piecewise exponential model, we got very similar estimates, actually. So you can see on this graph here, I plotted them all together. We have the hazard ratio across time since breast cancer diagnosis here again. So hazard ratio of hormonal therapy versus those not on therapy. And we see that they're all very similar, actually. The Weibull model is the one that's a little less similar, but otherwise I would still say they're all quite similar. So I guess in terms of choosing a model for this specific example, it's quite reassuring that we get robust results from the different models, which make different assumptions about the baseline hazard function. So let's also extend our model a little bit and say that we're actually also interested in adjusting for age at breast cancer diagnosis and the grade of the tumour that was detected. Then what we can do is we can just start by looking at our variables in our data set. We have a variable called AgeCat and a variable called grade 3. And we can use this codebook command in Stata to just have a look at these variables and give us some descriptives. So here we can see some output from this. For AgeCat, we can see that we have a range going from 0 to 2. It has 3 unique values. So we can see that this is a categorical variable. And we can see that we have, it goes from 0 to 2 here, which represent different age groups. So 0 is for 21 to 49-year-olds at breast cancer diagnosis. 1 is for 50 to 64-year-olds, and 2 is for 65 to 80-year-olds. And you can see the frequency presented here. And we see that there's 0 missing values in all of our observations. And then for the grade variable, grade 3, we have a label on this which says tumor grade is equal to 3. So this would indicate it's probably an indicator variable or a binary variable saying whether individuals had a grade 3 tumor or not. And if we look further down into some of this information, you can see that this is true. So we have a 0 value for 526. This is when individuals have a grade other than 3 cancer. And we have 161 individuals with grade 3. So that's what those two variables are. Age category in 3 different categories, and grade 3, which is an indicator variable for whether individuals had a grade 3 tumour or not. So if we wanted to adjust for those in our model, we just extend our model command that we had previously. We write STCox, that tells Stata we want to fit a Cox proportional hazards model. We have our exposure of interest hormone, which is hormonal therapy or not. Then we add our grade covariate here, which is for if you had a grade 3 tumor or not. And then we have an age category variable, which is 3 categories. And note that we use the I dot notation for all of these variables because they are categorical variables. And we have the no log option here just for some of the output to be shortened just for the slides. So here we see our output. And we get hazard ratios for all of our variables we include in the model. So the thing that we're most interested in is the hormonal therapy. That's our exposure of interest. And we see that the hazard ratio is 0.67, and the confidence interval goes from 0.52 to 0.587. And that compares those that had hormonal therapy to those that didn't. Now we also have a hazard ratio for grade 3. So the hazard ratio comparing those who had a grade 3 cancer versus those who had other grades. And then we also have age category hazard ratios, which are comparing the middle age category to the youngest, and then the oldest age category to the youngest category. So we can see that actually our hazard ratio doesn't change that much once we adjust for grade and age. We previously had 0.69, now we have 0.67. So once we've fitted a model, a Cox model, what we can do is we can estimate things from this. So there are some post-estimation of hazards that you can do from the Cox. As I said before, the baseline hazard function, the hazard rate across the timescale, is not directly estimated from the Cox model. You can see from the output that we only got hazard ratios. We didn't get any cons as we previously had, which shows us what our baseline hazard function is. But it is possible to estimate the baseline hazard function from Cox models. If we do this, then what we will have is a different hazard rate for every covariate combination, but each with the same shape, because we have hazard ratios that are constant across time. So what we can do is we can do this in Stata and have plots of the smoothed hazard functions across the timescale. And you can see here that these wiggle a lot. Here we've used a smoother that probably shouldn't be overinterpreted. So I've written at the bottom here, note that the shapes here should not be overestimated. But what I would sort of conclude from this is that the underlying hazard seems to increase across time until around 2 years, and then it decreases, and then it may pick up again after around 4 years. And the shape is constant for the shape is the same for every covariate. Here we have on the left-hand side hormonal therapy status. In the middle, we have the age at diagnosis groups. And then on the right, we have the grade of cancer. And you can see that irrespective of which group we're looking at, we see exactly the same shape. It's just shifted up and down. And that's just based on an assumption in our model. So if you want to predict these curves, you can use this command here, sdcurve. And what it will do is it will predict the hazard with this option, hazard here. And you can say at which values of which covariates would you like to predict at. So what I did to produce this curve is that I predicted firstly for the hormonal therapy graph, which is what is represented on the first line here, where we have an at 1 where hormone is equal to 0, and then at 2 when hormone is equal to 1. And then we run the command again, but we instead have the age categories here. So you can see I have 3 different at options. And then I create a graph in the third sdcurve for the grade variable. And then once I've created these 3 separate graphs, I use this command graph combine to create the combined graph as shown in the slide here. Now note that this command won't give you exactly the same format of graphs as I show in the slides, but in the do files that accompany the course material, you can get the exact code that includes all of the options to create the graphs exactly as they are in the slides. So that was everything for the Cox model. Here are some references if you would like to read them. And the next section, we'll start to talk about the proportional hazards model, proportional hazards assumption, and what it means to test for proportional hazards. We'll see you in the next section.